Okay, welcome back, students. Let's go over 4.6, basis and dimension. Okay, we're still wanting to answer the question, what's the minimum amount of elements, vectors, do we need to span a vector space? Okay, we talked last time about linear independence, and that is a part of getting us to the minimum number. If it spans and it's linearly independent, then that's going to be the minimum number of vectors that span a vector space. Okay, and we're going to find that minimum number is something called a basis. Okay, they're the building blocks for the entire vector space. So let's get into that. Okay. Okay, 4.6. Okay, is basis and dimension. Okay, definition. Okay, a set of vectors v1 to vk okay, in a vector space V is called a basis for V if the following hold true. A, the vectors span V. And B, the vectors are linearly independent. Okay, and this will create what's called a minimal spanning set. Minimum number of building blocks we need to span a vector space. Minimal spanning set. Okay, we've already are a little bit familiar with basis vectors from Calc 3. In R2, V1 is equal to 1, 0, V2 equal to, and V2 equal to 0, 1 are called the standard basis vectors. The standard basis vectors. Okay, likewise, in R3, V1 equaling 1, 0, 0, V2 equaling 0, 1, 0, and V3 equaling 0, 0, 1 are the standard basis vectors. Okay, and we recall from Calc 3 that V1 was called I, V2 was called J, and V3 was called K. Okay, where a random vector V is equal to AI plus BJ plus CK. Okay, depending upon what A, B, and C are. given A, B, C. Okay. Okay, so those were called the standard basis vectors. And now you know where the basis comes from. The basis is it is a base. It's the building blocks for the entire vector space of R3. Okay. For M2R, standard basis is E11, which equals 1000, E12, which is equal to 0100, E21, which is equal to 0010, and E22, which is 0001. So according to this, I can create any 2x2 matrix out of any linear combination of these four matrices. Okay, because it's just going to give me the first matrix is going to give me the first component. Second matrix is going to give me the second component. The third is going to give me the third, and the fourth is going to give me the fourth component. Okay, everything else would be zero. I would just add the zeros, and they wouldn't affect anything. Okay. So if I did a multiple of E11 plus a multiple of E12 plus a multiple of E21 plus a multiple of E22, I could multiply and create any value that I want in any of those four positions by doing a linear combination of these. Okay, let's do an example. Show that the polynomials P naught x equals 1, P1x equals x, and P2 of x is equal to x squared is a basis for P2R, okay, which is all second degree polynomials. Okay, well, we need to see, okay, does it span V? Can this span V? Well, if I take C times P1 of x plus B times P2 of x, no, I'm sorry. Let's do P naught and P1. C of P naught of x, there you go, plus B times P1 of x plus A times P2 of x, then that's going to be equal to C times 1 plus B times x plus A times x squared. Okay, and that's going to be equal to ax squared plus bx plus c, which is the standard form, okay, which is the general form, I should say, of any second degree polynomial. So P naught, P1, P2, okay, that set of vectors is a spanning set. It does span P2R. It is a spanning set of P2R. Okay, so that's the first criteria that is met. Second criteria that we need to have met is it independent? And we're going to use the Wronskian for that. we're going to do 1x and x squared, and then we need two derivatives because there's three items. So we need to create a 3 by 3. Okay. And so the derivative of 1 is 0, the derivative is 0, 0. X goes to 1 and then 0, and x squared goes to 2x and then 2. And I want to find the determinant of this, which is actually pretty easy to find because we have this row of zeros, this 1, 0, 0. So all I really need to do is look at my first column here, and if I do the first entry and get rid of row and column, this will become 1 times the determinant of 1, 2x, 0, and 2. Okay, plus 0 times the determinant of crossing off row and column. It'd actually be minus 0. Minus 0 times that determinant plus another 0 times whatever the determinant would be. But those are just going to go to 0. So that goes to 0 and that goes to 0. And so I'm really just left with this first value. And so this is 1 times 2 minus 0 times 2x. And so this just equals 2. Okay, because this will go to 0 as well. A lot of things going to 0. Okay, so this is equal to 2, which is not equal to 0. So we just need some value, okay, in the interval of negative infinity and infinity for all of these quadratics that doesn't go to 0, and we have one. We have 2. It does not go to 0. Therefore, in the interval negative infinity infinity, the polynomials one x and x squared are linearly independent. Okay, so that checks. Okay, since both criteria are met, okay, 1x and x squared is a basis for P2R. Not only is it a basis, but it's the standard basis. It's the simplest building blocks that we can get for all second degree polynomials. Okay, the set S equals 1 x and x squared is actually the standard basis of P2. Okay, we needed 3 vectors to do that. We needed 3 vectors, 3 components to give us the standard basis for P2R. Likewise, S equaling 1 x squared all the way to x to the nth power is the standard basis of Pn of R. Okay. We need n plus 1 items, n plus 1 vectors, n plus 1 elements to give us P of n of R. Okay, let's look at a theorem here. Okay. If a finite dimensional vector space has a basis consisting of n vectors okay? So if a basis has n vectors, then any set of more than n vectors is linearly dependent. The corollary to this, okay, all bases in a finite dimensional vector, finite dimensional vector space V contain the same number of vectors. Means that all bases are going to have the same number of items in it, same number of vectors. Okay, all the bases. If it's a basis with a certain number of items for one vector space, then it's going to be the same number of items for any base. Okay. Contain the same number of vectors. Okay, another corollary of the original theorem. Okay. If a finite dimensional vector space V, if finite dimensional vector space V has a basis consisting of n vectors, then every spanning set that for V must contain at least n vectors. Just saying that you can't get any smaller than the basis for a spanning set. You can get more to span vector space V, but you can't get any less. Okay, the basis is the lower bound. Okay, another definition. Okay, the dimension of a finite dimensional vector space V a written dimension of V is the number of vectors in any basis for V. Okay, so that's the dimension is the number of vectors in any basis. Since all bases are going to have the same number of vectors, then the dimension of V is that number of vectors that would create any basis. Okay, it could create the standard basis, or it could create any other basis. Okay. But any building blocks for the vector space are going to have a certain number of vectors, and that's called the dimension. Okay. The dimension of R2, as we saw, for the standard basis vectors of R2 was 2. The dimension of R3 was 3. Okay. So in general, the dimension for Rn would be n. Okay. We saw the dimension for M2R was 4 vectors. Okay. In general, the dimension for any square matrix, MNR, is equal to n squared. Okay. It's just n times n. Okay. Okay, the dimension for an m by n matrix in R is equal to m times n. This dimension. Or just mn. I'll leave the little dot there to signify that they're being multiplied together. Okay, and then what did we see with the dimension of P2R? How many was needed for that? Well, that was 3. And so in general, the dimension for PNR is equal to n plus 1. Okay, let's look at a theorem. Okay, if this is a biggie, if the dimension of V is equal to n, okay, if the dimension of the vector space is equal to n items, then any set of n linearly independent vectors in V is a basis for V. Okay, so I'll highlight this one. This one's a big one. Okay, it just says, look, if the dimension of V is n, okay, basically the basis for any spanning set in V is a basis for V has n items, then any set of linearly independent vectors. That's why we're interested in linearly independent. Okay, because you know, if it wasn't if they're not linearly independent, then they're not going to form a basis, because that's the definition of basis. But you know, they don't have to be special ones. This tells me that there are a ton of bases out there for any vector space. Okay, as long as they're linearly independent, we can show linearly independence, you know, using our techniques for finding the determinant. If the determinant is not equal to 0, or if A is invertible, then they're linearly independent, or if we can get the Wronskian not equal to 0. So we're building a bunch of tools in our tool belt to help us find if things are a basis for a vector space. Okay, if any linearly independent vectors are a basis, if choose any three vectors, as long as they're not linearly dependent on each other. I can't get one from the other two, or from two or more others. Then they could form a basis for the vector space. Okay, let's do an example. Okay, verify that 1 plus x, 2 minus 2x plus x squared, and 1 plus x squared form a basis for P2R. Okay, so let's check the number of vectors. Okay, so check, do we have the same number of vectors as the dimension of P2R? Well, what did we say the dimension of P2R was? Yeah, that's equal to 3. And do we have 3 vectors? Check. Okay, so that's good. Okay, now check for linearly independent. Okay, check linearly independence. Check linearly independence. Okay, and how are you going to do that with functions? Well, we're just going to do that with the Wronskian. So we'll do 1 plus x, 2 minus 2x plus x squared, and then 1 plus x squared. Okay, 1 plus x is going to go to 1 and then 0. 2 minus 2x plus x squared, that's going to go to negative 2 plus 2x. And then it's going to go to 2. Okay, 1 plus x squared, that's going to go to 2x and then 2. Okay. So now we just want to find the determinant of this thing. Okay. So cross off row and column and find the determinant. 1 plus x times, we cross off this row and column, we're going to get, and then we kind of get our cross products there. We're going to get negative 2 plus 2x times 2 minus 2 times 2x. Okay, that's for the first one. I'm going to put a minus sign because I know the next one has to be minus. Okay. For this, I'm going to use this top element there. So 2 minus 2x plus x squared times, okay, again, cross off row and column, and we get 1, 2, 0, 1, 2x, 1 times 2, 1 times 2 minus 0 times 2x. Okay, and then the last one is 1 plus x squared, that's a positive, times, cross off the last column, I get 1 times 2, 1 times 2, minus 0 times negative 2, that's just going to go to 0. Let me move this whole thing over real quick. Give myself a little more space on the paper. Okay. And then 1 times 2 minus 0 times -2 plus 2x. Okay, so let's clean this up. Okay. 1 plus x times inside here is going to be -4 plus 4x minus 4x. Okay, minus, okay, 2 minus 2x plus x squared times 2. Okay, that just goes to 0. Okay, and then plus 1 plus x squared times 2 minus 0. This just goes to 0 as well, times 2. Okay. Okay, and so we're going to distribute. Okay, and I get -4 plus 4x minus 4x minus 4x. Well, you know what? I'm going to simplify first because I don't have to distribute. The 4x and the 4x are going to cancel, which is nice. Okay, so that's just going to get me -4. So that's a whole lot easier than distributing all that stuff there. So distribute -4, I get -4 minus 4x. Okay, that's nice. Okay, distribute -2, the minus and the 2. Through all this, I'm going to get -4 plus 4x. Okay. And then minus 2x squared. Okay, and here I'm going to get, distribute the 2, I'm going to get a +2 and a plus 2x squared. Okay, so look at that. All of the variables go away, which is nice. And I'm left with -6, which is not equal to 0. And so since the Wronskian is not equal to 0, it's linearly independent. Okay, and so therefore, one plus x, 2 minus 2x plus x squared, and 1 plus x squared do form a basis, are a basis of P2R. Okay, one last theorem here. Okay, let S be a subspace of a finite dimensional vector space V in any basis for S is part of a basis for V. For V. Again, we could use our Venn diagram here. Okay, if I get a basis of S, say that, you know, 2 vectors is the basis for S, and that's a subspace of vector space V, then those are going to be part. Those are part of a basis for V. We would need an extra component or components, extra vectors to give me but I could use what the basis for S as a starting point to find the basis for V. Okay, and that's it for 4.6.